Welcome back everyone to this lecture on the supervised machine learning process. The first half of machine learning algorithms we're going to be learning about fall under the supervised learning umbrella. So what we want to do is really focus on the philosophy and details behind supervised learning, including things in the process like the train test split and performance validation, as well as hyperparameters adjustments. So what we're going to do here is just see how supervised learning fits into the overall machine learning pathway and the specific details behind supervised learning. That way, when we're actually coding this out with things like scikit-learn and Python, we don't just see these ideas for the first time. Instead, we have a philosophical understanding of why we're actually performing the tasks in Python. So as I mentioned, let's take a look at this within the entire machine learning pathway. We know that we're going to collect and store data from the real world. Then we can clean and organize that data, and then we can perform exploratory data analysis, things like statistical analysis or just visualizations. Then if we want to move beyond data analysis and actually create a data product, that's where we're going to need machine learning models. For supervised learning, where we're predicting an outcome, or unsupervised learning, where we're discovering patterns in data. And as far as Python is concerned, we know for the data analysis portion, we have Jupyter, NumPy, Pandas, Matplotlib, and Seaborn. Then when it comes to the machine learning models section, we actually have this very large and powerful library called scikit-learn available to us. And so what we want to do right now is focus on what's actually going on when we talk about supervised learning, predicting an outcome. This machine learning models block in the entire pathway actually contains many sub-steps within it. So what we're going to do is really focus on what's happening when we talk about supervised learning. And we're going to call this the machine learning process for supervised learning tasks. Later on in the course, we'll go over the machine learning process for unsupervised learning. But the first half of algorithms we encounter are all falling under supervised learning. So let's take a deeper dive by taking a look at the example problem that we keep referring to, which is trying to predict the price a house should sell at. So what we're going to need to do is start with collecting and organizing a dataset based off history. So that means we're going to take a look around our neighborhood at prices that we know houses have been sold at in the past. And we take some note of their features, like their area, bedrooms, bathrooms, and then the historical price that they sold at. Note here is that we have a historical labeled dataset on previously sold houses. And then what we're going to do is try to create a data product that can help us with the task of predicting what price a house should sell at. So at the end of the day, if a new house comes onto the market, we want to know if we know the area, bedrooms, and bathrooms of the house, what price should I list it at, based off what I know about historically sold housing. So for a data product, you always have some sort of input and output. In this case, we have the input of house features and the output of hopefully the predicted selling price. So we're using historical labeled data to predict a future outcome or result, which essentially is the definition of supervised learning. So let's take a deeper dive into all the subsets that are going to happen within this supervised learning process on predicting the price a house should sell at. So we already know that we have that data. We run around and we grab that historical data on the features of a house and then the predicted price. The next step for supervised machine learning process is to separate that data into features and label. And you'll notice here that I said X to features and Y to label. Don't worry too much about that notation right now. Later on, we'll discover as we essentially map out this process to mathematical matrix notation that we typically label features as the X matrix and the label as the Y. But for right now, let's just go and have an overview of what are features and what is the label. So we already know we have this entire data set. And what we need to do is understand the label. The label is just a term for what are we trying to predict. And in this case, we know we're trying to predict the price of a future house, which means the price column is going to be the label itself. Then we know features are the known characteristics or components in the data that we're predicting the label from. In that case, it's all the features of the house, such as the area, the number of bedrooms, and number of bathrooms. And now we've taken our complete data set and we've assigned the features that we're predicting from and the label, what we're trying to predict. And so we can notice here, we have labeled historical data. We know all the features that correspond to the label or price that house sold at. Now the next step that is absolutely critical to the supervised machine learning process is this training test split. So what we end up doing is once we've identified features and label, we split the data into a training set and a test set. Keep in mind, later on in the course, we're going to discuss more advanced methods of this, generally called cross-validation, and we'll also talk about holdout sets. But for right now, let's take the simplest approach, which is splitting into two sets, a training set and a test set. So the obvious question then is, why are we performing this split? And how do I decide how to split up this data? Well, in my personal opinion, the easiest way to understand this is by taking a step back from judging an algorithm and deciding how would you actually judge a human's performance on choosing a selling or listing price for a new house on the market. So let's imagine you have a friend who is a human realtor. Well, how would you judge a human realtor's performance if you had an existing data set and a new house that you wanted to put on the market? So what you could do is you ask your human realtor to take a look at the entire historical data set. You give them the features and then the price that these houses have sold at in the past. And you want their help for choosing the price for a new house on the market. So after giving her the features of the house, we want to ask her to predict that selling price. But the problem is, how do we actually measure how accurate her prediction is? And what house should we choose to test her on? Unfortunately, we can't actually judge her based off the brand new house because it hasn't sold yet. We don't actually know what the correct true selling price is. And it's not going to be very useful to us if we judge her performance after we sell this new house, because then what was the point of actually having her help to begin with? So what we want to do is be able to judge her performance before we decide on a price for that historical house. Now the problem also occurs is that we can't really judge her on the data that she's already seen, because in theory she could have just memorized the entire data set and thus have perfect accuracy when recalling what the price of a house sold at. And this is where the need for the train test split comes into play. Basically the idea is we want to be able to fairly evaluate the performance of both our human realtor or later on our machine learning algorithm. So let's think about how we're actually performing this train test split. So we already organized the data into features that we're calling X and the label that we're calling Y. And what we're going to do is split this into a training set and a test set. This way we can feed the training set to our human realtor or our algorithm, have them learn off the training set, and then evaluate them off data they haven't seen before, which will be the test set. So notice here that the training set and test set both grab the features and the labels. And typically you decide on some sort of percentage split. And it's really common to have most of the data be falling under the training set and have some of the data fall under the test set, such as 70% for training and 30% for test. But we'll discuss in much more detail how to decide on those splits as well as more advanced methods of performing these splits. But the main idea is we're going to show the algorithm some training data and then evaluate the performance on some test data. Keep in mind that if we really thought about this, we actually have 4 components. We have the features for training and the label for training, that is X-train and Y-train. And then we also have the features for testing, X-test, and the label for testing, Y-test. So keep in mind later on when we're coding this out with Python, we'll actually see this labeled as 4 separate components. Even though technically we only have one training set and one test set, we could separate this out based off the features. So we have X-train, Y-train, and X-test, Y-test. And this further separation into 4 components actually becomes important later on when we evaluate the performance. So let's go back to fairly testing our human realtor on this. We take the training test as well as the test set. And then what we're going to do is we're only going to let the human realtor study and learn on the training set. We give them access to both the features and the label of our training set, so they can see the relationships between area, bedrooms, and bathrooms and the historical price the house sold at. Then when it comes time to actually evaluate her skills on choosing pricing, what we're going to do is, since she learned about the data in the training set, we can now test her skills on the test set. But notice all we're going to do is feed her the features from the test set. So after she learned on the training set with both features and labels, what we can do then for this human algorithm is say, hey, here are some new features. What price do you think these houses should sell at? And so we provide only the X-test data and ask for the predictions on the sell price. This is new data that she has never seen before. And she has also never seen the real sold price here. So we know we don't have this issue of her possibly memorizing this data. And so what we do is we ask her for predictions per data point. And now she's predicted the price that these houses should have sold at in the past. And then what we can do is bring back the true original prices that they sold at. And then finally, we're going to compare the predictions against the true price. And we'll have a much deeper discussion on the different mathematical ways of comparing a prediction versus a price. In general, this is often labeled as y hat for your prediction and y as the true test price. And you'll notice here that in general, we can say she's off by an average of $10,000. So later on, we'll discuss many methods of evaluating the performance, but the main idea here is that we're actually able to now fairly evaluate this human realtor or our machine learning algorithm with the use of a train test split. And now that we understand the train test split, let's go ahead and continue with the rest of the supervised machine learning process. After we split the data into a training set and a test set, we know that we fit and train the model only on the training data set. Then we fairly evaluate its performance by feeding into the model the features of the test set and comparing the model's predictions to the known test set label. Now the question arises, what happens if you're unsatisfied with the performance of the model's ability on the test features? Well, we can adjust what are known as model hyperparameters. Essentially, many algorithms have adjustable values. So what you end up doing is, if you're unsatisfied with the performance on the test set, you can go back and adjust your model's parameters. Then you retrain the model on the training data set and evaluate this adjusted model again on only the features of the test data set. And you can repeat this process as necessary. So for the full and simplified process of the entire supervised learning, what we have here is we get our data, separate it out into features and a label, then split the data for evaluation purposes into a training data set and a test set. We fit and train the model on the training data set, and then we evaluate model's performance on the test data features and compare its predictions to the known y-test label. Then we can adjust model hyperparameters as needed and essentially repeat that process of training the model, adjusting it, evaluating its performance as necessary. Once you're satisfied with the model, you can deploy the model to the real world. So that is the supervised learning process for machine learning models. Then you can deploy the model as a service, a dashboard, or application where you've then created a data product to hopefully predict future outcomes or gain insights on data and then have that executed out in the real world. And now we have a full understanding of the machine learning pathway for supervised learning models. Thanks, and I'll see you at the next lecture.